Okay, so we're going to do the last example, example 3. And you were asked the approximation of ln of 1 plus x is approximately x minus x squared over 2 is used when x is small. Use the Lagrange form of the remainder to get a bound for the maximum error when the absolute value of x is less than or equal to 1. Okay, and so we're going to support the answer graphically. Alright, so in the notation of the remainder theorem, we are given a second polynomial or a second order polynomial. That's this. And so we need a bound for the absolute value then of R2 of x. And we're talking about on the interval negative 0.1 to 0.1. So if we were looking at our next part of the remainder theorem, we would need to find the third derivative of ln of x. So I'm going to call that f3 of, we can use c or t, really we're just picking a different value other than x because this is not in general. This is a specific t value on that interval. If you would go through, the first derivative of this is 1 over x, the second derivative is negative 1 over x squared, the third would be then 2 over 1 plus, in terms of t to the cubed. If you were to graph this function, what you would find is this is a decreasing function. So it's decreasing, and therefore on any closed interval it would have a max value at its left endpoint. Okay, and so when we pick that, that capital M that we were using with the remainder estimation theorem, we can use as our M, our maximum, whatever we get when we plug in that left value of the endpoint, because that would then be a maximum bound for the remainder. So I do that. So I have 2 over 1 plus negative 0.1, and that's to the third power, and we need to make this an absolute value. When we do this, you get, let's see, this is 2, 1 minus 0.9, then 0.9 to the third, 0.9 is 9/10. So the fraction value is 2,000 over 729. I'll let you go at the exact specifics, but essentially we have 2 over 9/10 to the third power. Okay, so once again we can let r equals 1. Again, I'm not sure why we let r equals 1. I'm hoping that it'll become a little more clear in the next section. But according to the remainder estimation theorem then, what we can say then is we have this m value, the remainder can be bounded or is less than or equal to this max, which is, the absolute value of that is still 2,000 over 729, times the absolute value of x to the third over 3 factorial. And so what happens then is that is going to be less than or equal to 2,000 over 729 times, if I would put in that left and right bound, plus or minus 0.1 to the third over 3 factorial. And what I get then is a value for that using my calculator, and I'm going to round up a little bit to be safe, so I'm going to round up to 4.6 times 10 to the negative 4th. Rounding up is always going to give us a little bit of leeway if we're talking about a max error. Alright, I'm just checking this math here. Yeah, so if we would do that, I end up getting the 4.6 times 10 to the negative fifth, but then I rounded up 1 decimal point just to be safe. Okay, in looking at the graph, and by the way, we can do the remainder estimation of just this function R2 of negative 0.1 if we wanted to by using the third derivative function. Okay, anyways, so the question is to use the Lagrange form to get a bound for the maximum error. This would then be my bound for my maximum error using the Lagrange method. You can look also at the graph and just kind of verify some of the things we were talking about. If you were taking a look at the remainder R2 of x, you could just get that by taking the function, which is ln1 plus x, minus the remainder, or sorry, the error, and then you plug it into a graph. What you find is it does almost have some like odd symmetry to it, and you can even graphically take a look and find the maximum and find or confirm that it is less than that bound, and that's what we're looking for. So there's a little bit of how to use the Lagrange form of the remainder to get a bound for the maximum error.